Back to some limiting reagent problems. This one's a little bit different than what we've done before because in this one, not only are we going to calculate the mass of water again, but we're also going to be figuring out which reagent is in excess and how much is left over. So let's just do the first part to calculate the mass of water using the two givens. So the first one, we want grams of water when we have 24.0 grams of hydrogen. So my first step is going to be to take my 24 grams of hydrogen times 1 mole over 2.0 grams, which is the molar mass. Now I want water, so my second one is going to be the mole ratio of 2 moles of water to 2 moles of hydrogen from the balance equation. And again, our last step, only because we keep using water, is the molar mass of water of 18.0 grams per mole. We look, all of our units cancel. I go grams to moles over grams, to moles of water over moles of hydrogen, to grams of water over moles of water. I do my math, and I get 216 grams of water. So if I use 24 grams of hydrogen, I would produce 216 grams of water. Now we have to figure out what 160 grams of oxygen would do. Now looking at this, there's a lot less hydrogen than oxygen, so you might just assume that hydrogen is the limiting reagent, but we have to prove it with our 160 grams of oxygen. So the first step, we take our 160 grams of oxygen times 1 mole over the molar mass of 32 grams of oxygen. This time our mole ratio is 2 moles of water to 1 mole of oxygen from the balanced equation, and the last step, once again, must be the same so we can figure out and compare our grams of water. So 160 times 1 mole over 32 times 2 over 1 times 18 over 1 gives me 180 grams of water. So believe it or not, even though there's a lot more oxygen, that 160.0 grams of oxygen is our limiting reagent. Now the second part of this is it asks for how much of the excess reagent is left over. So I have here, we want grams of excess reagent using our limiting reagent. So our limiting reagent is the 160 grams of oxygen, as you see above. So my first step is going to be the same as the first step I did in the previous problem. I have to convert my grams of oxygen to moles of oxygen. This time, instead of solving for water, I'm going to solve for moles of H2 because I want to know how much H2 is left over. So then my last step would be 2 grams of H2 over 1 mole of hydrogen. This way my units cancel, I'm left with grams of hydrogen. When I do the math, 160 times 2 divided by 32 is 20 grams of hydrogen. Now what I'm getting is if I use 160 grams of oxygen, as we did because we circled that equation, I would need 20 grams of hydrogen. But if you look at the original problem, I have 24 grams of hydrogen at the beginning, but in order to use up the oxygen, I needed 20 grams, so that would give me a 4.0 gram remainder in excess of hydrogen. So that's the only other thing that you would do with a limiting reagent problem is to figure out which reagent is limiting and how much of the other one remains. Okay, number 3, 18 grams of carbon reacts with 18 grams of oxygen, which is the limiting reagent, and how many grams of carbon dioxide will be produced? So finally, we're not dealing with water. We have carbon plus oxygen yields carbon dioxide. We have 18 grams of carbon. We want to figure out how many grams of carbon dioxide. So step 1, we take our 18 grams of carbon times 1 mole over 12.0 grams, the molar mass of carbon. The second step, I'm going to go to moles of CO2 over moles of carbon, and it's 1 to 1 from the balanced equation. And the last step is I want grams of carbon dioxide, so the molar mass of carbon dioxide is 44.0 grams. And I do my math, 18 times 44 divided by 12 gives me 66.0 grams of carbon dioxide. What that means is if I use all 18 grams of carbon dioxide, I'll make 66 grams of carbon dioxide. The second one, I'm going to use 18 grams of oxygen and figure out how many grams of carbon dioxide I would form. So the first step is to take my 18 grams of oxygen, convert it to moles, 1 mole over 32.0 grams. Second step, my mole ratio now is 1 mole of carbon dioxide over 1 mole of oxygen from the balanced equation. And my last step again is going to be the same as the previous, so we can compare, and it's 44.0 grams of carbon dioxide per mole. 18 times 44 divided by 32 gives me a 24.8 gram yield. So that obviously is telling me that my 18 grams of oxygen is my limiting reagent because it only is going to make 24.8 grams of carbon dioxide. In this one, it does not ask you to figure out how much carbon is left over, so we don't need to. The next thing we're going to do is called a limiting reagent worksheet. This is a visual explanation of a chemical reaction. So we're going to use this to see if you can truly understand. Maybe with graphics you can see what limiting reagent is really talking about. So we look at the graphic, and on the left side at the top it says 3 nitrogen molecules. Underneath it says that's 6 nitrogen atoms because 3 times 2 is 6. We have 3 hydrogen molecules, which is 6 hydrogen atoms. On the right side, when the 3 nitrogens react with 3 hydrogens, we get 2 ammonia molecules, which is NH3, and we get 2 excess molecules of nitrogen. Notice, on the left side, the 6 nitrogens, only 2 of them are in the product of ammonia. The other 2 molecules are left over. If you look on the left side, the 6 hydrogen atoms are all in the ammonia molecule, so there's no excess oxygen in that. So let's start this. How many nitrogen molecules are shown? 3 molecules on the top, 6 atoms below. Hydrogen, 3 molecules on the top equation, 6 atoms below. What is the ratio of nitrogen to hydrogen in NH3? Well, in NH3, there are 3 hydrogen atoms per molecule because it's NH3, so there's 1 N and 3 H's. How many H's would be needed to react all of the nitrogens? Well, all of the nitrogen up there would need 18 because 2 of them will use 6 to make 2 molecules, but I still had 4 left over. So each of those needs 3 more. So those 4 nitrogen atoms that are left there, each needs 3 more hydrogens. So 3 times 4 would be 12 more plus the 6 that we started with. So you would need 18 total hydrogen atoms to make this a non-limiting reagent problem. How many nitrogen atoms would be needed to react all of the hydrogen atoms? Only 2. Because you look on the left, all the hydrogen atoms are in molecule, and there's 2 nitrogens that cause those 2 molecules. According to your answers to 4 and 5, how many nitrogen molecules and hydrogen molecules will be used up completely? 1 nitrogen molecule and 3 hydrogen molecules were used. That's how I got my 2 molecules of ammonia. Which reactant will remain and how many? As you see on the right, there are 2 nitrogen molecules that are left over at the end of the reaction at the top. Number 8. Number 8 shows reactant 1 and reactant 2. The large reactant 1 atom and reactant 2 molecules are going to form a product that has 2 of the large reactant 1 atoms and 6 of the reactant 2 atoms. So if you look at that, on the left side, I have 6 of the large molecules, or I'm sorry, 6 of the large atoms and 6 molecules. But remember, the product is going to use 2 atoms from reactant 1 and 6 from reactant 2. So on the left side, I have the ability to make 3 molecules of the product if I have enough of reactant 2. But I look at reactant 2, I have 2, 4, 6, 8, 10, 12. Well, each one of those needs 6, so those 12 are only going to end up making 2 of the product. So when I do this, you see that there are 2 products, which then take up 4 of the atoms from reactant 1 and all 12 of the atoms from reactant 2. So if you look at that and you start crossing them off on the left side, that leaves you 2 left over of reactant 1 atoms. So which reactant in the diagram is the limiting reagent? Reactant 2, the molecule of the smaller atoms, because there are none left on the right side. So which is in excess? Reactant 1, because there are 2 left over on the right side. The final thing we will talk about is percent yield. Percent yield is when you're dealing with the products. Up to this point, limiting reagents, we've been dealing with the reactant side. Percent yield is going to deal with the product side. The expected yield, which is also called the theoretical yield, is the value obtained for a product's amount when doing calculations using the equation. This is the maximum amount of product that could be formed. We call that the theoretical yield. So all of the numbers that we've been getting so far, if they've been for products, those have been theoretical yields. Using the theory of stoichiometry, you should get that much. The actual yield is the amount of product that forms when a reaction is actually carried out in lab. Rarely do you get 100% yield. There's usually something going on in the lab that would keep you from getting 100% yield. Well, the percent yield is the ratio between what you actually get in the lab versus what you theoretically should get using stoichiometric calculations. This, in essence, measures the efficiency of the reaction. The higher your percent yield, the better your results are. All right. First problem. If 20 grams of phosphorus reacts with excess oxygen, so we already know there are 20 grams of phosphorus as our limiting reagent. That's why I said with excess oxygen, meaning you're going to use all 20 grams of phosphorus. What is the percent yield if 0.278 moles of diphosphorus pentoxide is produced? The balanced equation is 4P plus 5O2, yielding 2P2O5. So look at these steps. Step 1, convert the 20 grams of phosphorus to moles of phosphorus. Step 2, use the mole ratio to convert to moles of diphosphorus pentoxide. Notice there's no step 3 because it's looking for the percent yield in moles. If it was looking for the percent yield in grams, we would have to do step 3. But when you see that you set up the problem, when you are done crossing off all of your units after step 2, you will be at moles of P2O5. As it says, since you're solving for moles, you're done with this part. So what we're going to do is we're going to take our 20 grams of phosphorus times 1 mole over 31.0 grams of phosphorus molar mass. Second step is 2 moles of P2O5 over 4 moles of phosphorus. Notice there's no step 3 because it's asking to compare the 0.278 moles to the theoretical, which we're about to get by taking 20 times 2 divided by 31 divided by 4. And that theoretically is going to be 0.323 moles of P2O5. So now what we're going to do, the actual moles is 0.278. So to do our percent yield, we're going to take our actual divided by our theoretical times 100. So we're going to put the 0.278 moles, which was in the problem, divided by our 0.323 moles, which is the theoretical using stoichiometry. So when you do the math, 0.278 divided by 0.323 times 100 gives us an 86.1% yield. That's pretty good. When you're doing this, you can never have an actual yield greater than the theoretical yield because that would mean you're getting more out than is possible according to the law of conservation of mass. The second one, the burning of 18 grams of carbon produces 55 grams of carbon dioxide. What is the theoretical yield of carbon dioxide? Calculate the percent yield of carbon dioxide. Well, there's something missing here. We're missing the reaction. The burning of carbon produces 55 grams of carbon dioxide. Well, we know burning is a combustion reaction, so our reaction is carbon plus oxygen gives carbon dioxide. So now we have our balanced equation, all one mole. So now we're going to take our 18 grams of carbon, as we always do. We're going to convert that to moles, step 1. Then we're going to use our mole ratio of 1 mole of carbon dioxide over 1 mole of carbon from the balanced equation. And we're going to use the 44.0 grams of carbon dioxide, which we've calculated before as the molar mass. Now when we do the math, 18 times 44 divided by 12 gives us a theoretical yield of 66.0 grams of carbon dioxide. Whenever you're doing stoichiometry, that's theoretical. Now, according to the problem, it only produced 55 grams. So 55 grams is our actual yield. So to do our percent yield, we're going to do the 55 grams in actuality versus the 66 grams in theory. And that gives us an 83.3% yield. Number 3, calculate the percent yield of chlorine in the electrolytic decomposition of hydrogen chloride if 25 grams of hydrogen chloride produces 13.6 grams of chlorine. Well, hydrogen chloride is HCl, so the only way you can decompose HCl, you're going to get hydrogen and chlorine. So there's our balanced equation. So now what we're going to do is we're going to do this as if we were doing any other problem. We're going to take our 25 grams of HCl, convert it to moles. The molar mass of HCl, 36.5. The second step is we want to figure out the percent yield of chlorine. So we're going to use 1 mole of chlorine from the balanced equation over 2 moles of HCl. We're not really concerned with the hydrogen at this point because it's not asked for in the problem. And we want grams of chlorine so we can compare it to the 25.8 grams. So the molar mass of chlorine is 71.0 grams. I do my math, 25 times 71 divided by 36.5 divided by 2, and that gives me a theoretical yield of 25.1 grams of chlorine. Now, to do the percent of the chlorine gas, we're going to put the 13.6 grams over the theoretical 25.1 grams, and that's only a 54.2% yield. You'll notice that all the percent yields, when we use stoichiometry, that's theoretical. The actual yield either must be given in the problem, or they would have to give you the percent yield and you would calculate it using percent times the theoretical yield. Little algebra there. In a particular reaction between copper metal and silver nitrate, 12.7 grams of copper produces 38.1 grams of silver. So if the 12.7 grams of copper is there, but silver nitrate is not listed, that must mean that the 12.7 grams of copper must be our limiting reagent. Our 38.1 grams of silver is our actual yield. So what we're going to do is we're going to convert our 12.7 grams of copper to moles using the molar mass. Then we're going to put 2 moles of silver over 1 mole of copper from the balanced equation. We're going to follow that with the molar mass of silver of 17.9 grams. We're going to do our math. 12.7 times 2 times 107.9 divided by 63.5 comes out to 43.2 grams of silver theoretical. Our percent is just going to be our 38.1 grams divided by our theoretical of 43.2 times 100, which comes out to 88.2% yield. All percent yields are done the same way. You just have to make sure that you're solving for the right thing and making sure, as always, that all your molar masses are correct. The last thing, using mole ratios in a stoichiometry worksheet. Mole ratios relate